Okay, so what I want to talk about today, here's kind of the deal. We're going to go through a couple new things. It's not a big deal. This is a really simple kind of couple sections here. It's based on, I wouldn't even probably do this if it weren't in an honors class. I want you just to get used to some logic statements, and that's really what this is about. It's going to lead us into maybe some really simple proofs. I'm not going to spend a lot of time with proof. With you guys, I'm going to do some, but I'm not going to do a ton just because the research shows it's really not that valuable. But I want you to see some of it. So this is not like stuff we've done with. This is more, it's not even going to sound like math to me. It's going to sound more like a discussion of logical thinking. So that's kind of where we are. All right, so conditional statements. Conditional statements are statements that we deal with in math that allow us to state something in terms of a hypothesis and a conclusion, right? So it's got two parts, hypothesis and conclusion. The thing about these is we can always write these as causal. We can write them as if-then statements, which means, if this, then that, right? And we want to do that. That's in when we're doing proofs, we always want to write them in if-then form. So the hypothesis is always going to be the first part, just like it would be in science, right? We're going to have an if followed by our hypothesis or the hypothesis, and the then part becomes the conclusion. They don't always start off this way, but that's one of the things I'm going to have you do is I'm going to have you take a conditional statement that's not written that way and write it that way. Okay, so the assignment really is a lot of stuff like this, where you've got some kind of a sentence and you need to rewrite the sentence in a logical way. So this is an example of a situation like that where we have a conditional statement written in if-then form. If you are a brunette, then you have brown hair. True, right? Okay. There's the hypothesis, there's the conclusion. Okay, hypothesis, you're a brunette. Conclusion, you have brown hair. Okay, what about this one? This one is not written in if-then form, but it is a conditional statement. Any ideas how we could say this? What do you think?
If angles are vertical to each other, then they are congruent.
Something like that, sure, right? So we're saying if, kind of not grammatically correct, but just think about it conceptually this way. We're saying if vertical angles, then congruent, right? So we'd have to make that grammatically correct and say something like if two angles are vertical angles, then they are congruent, or something along those lines. And there's no one right answer here, right? But you see the point we're making. We want to write it in the form of an if-then statement. So this is just an example of a way we can do it. This is not by any means the only way. If there are two vertical angles, then they are congruent, something like that. But what Helmut, you said was fine too, I thought. That was equivalent to this, okay? So, make sense? Okay. Try this one. I don't you have to write it down. Just see if you can think about how that's going to be. Suggestions? Yes.
If it weighs 2,000 pounds, then an object weighs 1 ton.
Okay, good. Yeah, and notice that's good because notice that the word "if" did appear in that, didn't it? Right. So that gives us a clue that this really needs to be the hypotenuse, right? This is the part that we're saying it's if this, right? That's the hypotenuse. Then there's going to be some conclusion, right? So probably you'd want to say just to make this just a slight tweak on that. You'd probably want to use the word object in the always in the hypothesis, right? So you probably want to say if an object weighs 2,000 pounds, or then it's 1 ton. Then it weighs 1 ton or something like that, right? Does that make sense? Okay. Okay. Counterexamples. What's a counterexample? Yes, ma'am.
It's an example to show that this is false.
Okay, good. It's an example that disproves something, right? The nice thing about math is a lot of times when we're doing formal proof in math, all it takes is one counterexample to disprove a statement, right? And so it's something that we're gonna use. It's not an example of something showing that it's right. It's an example showing that the logic is flawed. The statement is incorrect. Okay, this is important. With the counterexample, it must be consistent with the hypothesis. So it must essentially start with the same hypothesis, but it's got to show that the conclusion is not necessary or is false, right? So for example, and that's, 3 times because that's so important. That's one of the things that people really have trouble with when they want to come up with a counterexample, is sometimes they'll try to change the hypothesis, and that's not valid. It has to keep the same assumption, but show that that assumption is flawed, okay? So for example, we got to find a counterexample here. We want to find an example that shows that this conditional statement is false. What's the hypothesis here? What do you think? Okay.
But the hypothesis is x equals 9. Well, I was going to say it could be plus or minus 9.
Yeah, okay, and you're right. That's the answer. So there's the answer. Now, what's the hypothesis, though?
X squared equals A squared 1.
Okay, x squared equals 81, right? If x squared equals 81, so when we come up with a counterexample, I can't pick the example x equals 10, right? Because everybody see that's not valid. Yeah, I mean, sure, there are numbers that don't equal 9, but just any number that doesn't equal 9 isn't good enough. It's got to be a number that doesn't equal 9, but that also honors that claim, that x squared equals 81, right? And so Duncan's right. We got to keep that hypothesis, but find a conclusion that's different than this. So the counterexample would be x equals negative 9. Make sense? Okay. Okay, negation. What do you think it means to negate something? Negative. Okay, yeah, it's going to negatify it, right? It's going to make it negative or make it the opposite, right? So we can negate things. We negate things in math all the time. It's just the opposite of a statement. For example, negate x equals 3. No, not necessarily. Because x equals negative 3 would be one example, but x does not equal 3. Yeah. Typically, when you negate something, all you're doing is you're adding the word not somewhere, right? This, by the way, I'll also tell you, this is the kind of thinking that you do when you write computer code. Computer code is completely logical. It's all based on certain kinds of loops and statements, if-then statements, things like that. For this particular condition, do this thing in the program. All that stuff is just, it's very, very similar to this. And the same kinds of thinking that you do when you work with logical statements in math. And I think I'm going to eventually show you truth tables. You know what that means in math, what a truth table looks like. They look identical to the kinds of truth tables you use in programming. I'm not going to do it today, but you'll be interested in that. So there's the negation of x equals 3. X does not equal 3. That is, by the way, a real math symbol. Not equal to is an important math symbol, right? Negate x or negate t is greater than 5. Say it again. Okay, what would that mean though? So if it's not greater than 5, what's another way of saying it? Less than or equal to 5. Yeah. If it's not greater than 5, then it must either be 5 or less than 5. So it's less than or equal to. Very good. Okay, converse. So negation just makes something not true, right? It's essentially including the word not. Converse. We want to take a stab at what you think a converse might be. What's it? Anybody have an idea? Yeah, you're gonna flip things, aren't you? The converse is when you're gonna kind of reverse in order. So if we've got something like an if-then statement that comes with a hypothesis and conclusion, all we're going to do if we want to write the converse of that statement is create them. That's it. Okay. Are converses always true? Well, let's look at an example of one first. What would the converse be if you are a brunette, then you have brown hair? Okay, is that true? That's true. Are converses always true?
No.
Can you come up with an example of my challenge. See if you can think of an example of a statement whose converse is false. Yes, ma'am.
If it is a square, then it is a
Is that what you're gonna say? If it is a square, then it is a rectangle. Very good. If it's a square, then it's a rectangle is true, correct? But if it's a rectangle, then it's a square is not. Very good. Okay? Make sense?
It's first grade math.
Okay. Inverse. What do you think an inverse is? Yeah, okay, not exactly. The converse was when we flipped the hypothesis and the conclusion. An inverse is when we negate both. Okay? So, an example would be, you tell me, write the inverse of, if you are a brunette, then you have brown hair. Or just you can just say it. Matthew, what's going to be the inverse of that then?
If you're not a brunette, then you don't have brown hair.
Yeah, okay. Now, what about this one? If the original conditional is true, is the inverse true?
Yes.
It is. Yeah, that's true. Okay. Okay, contrapositive. What do you think the last of the three I'm going to show you is then? Yes, ma'am.
Oh, where you add
No, not quite. Not quite. You're thinking of biconditional. Yeah. What do you think? Yes, ma'am.
It's the opposite, but it's still right.
It's the, okay, kind of. It's going to be the combination of the two,
Yeah.
right? The contrapositive is going to be you're going to take the converse of a statement, the converse of the inverse of a statement. So you're going to flip the hypothesis and the conclusion and negate them both, right? So then what's going to be the contrapositive of this statement? If you are brunette, then you have brown hair. So Gabe, what's that going to be? I'm going to do both at the same time.
If you do not have brown hair, then then you're not a brunette.
Yeah, if you do not have brown hair, then you're not a brunette. Right, exactly. Okay? Perfect. Oh, you know what? I think that's actually the true statement. I think you can come up, I think I told you something wrong there. I did. The inverse is not always true. You could come up with examples where the inverse is false, but the contrapositive, that's not the case. If the conditional statement, the original conditional statement is true, then the contrapositive is always true because they have the exact same meaning. They mean the very, very same thing. If you look at it in terms of, I don't have time to do it today, but we'll take a day. If you look at it in terms of like set theory, like a Venn diagram, if you look at the sets of stuff that's included in a conditional statement, you'd find, if you explore it that way, that you're talking about the exact same sets when you look at it this way, okay? The converse and the inverse always have the same meaning. We'll take a little bit of a further look at that later. What I want to also quickly look at today is just what happens in certain cases. There we go. Okay, definitions and biconditional statements. And all this is really going to be, we're just looking at kind of some basic definitions. You'll get a little bit of chance to just do the stuff we just did. But there's very little kind of algebra type math here at all, even geometry type math. So, what's a definition? A definition is, here's an example of a definition. Perpendicular lines are those which intersect if they form a right angle. Okay. You could say a line perpendicular to a plane is a line that intersects the plane in a point, and blah, blah, blah. I mean, these are just examples of, we'll look at these in more detail later. But with a definition, I want you to notice that you can read it either way. Definitions are true front to back or back to front. Okay, that's always the case. You can read it forward, you can read it backward. The definition of perpendicular lines means if two lines are perpendicular, then they intersect to form a right angle, or you could say if two lines intersect to form a right angle, then they're perpendicular. They work equally well with the definition. Okay, that is a type of statement that we call a biconditional statement, because we can look at it in either direction, right? In the first statement here, what's the hypothesis? Two lines are perpendicular. The conclusion? Yeah, they form a right angle. Bottom one, we flip it, right? The hypothesis is they form a right angle. Conclusion, they're perpendicular, right? So that's a biconditional statement. So real quick, there's no X on here. The X on here. X is the intersection. What do you think? Are true or false? Points DX and B are collinear. Yeah, they are, right? Is AC perpendicular to DB? Based on what we just briefly talked about. How come? Yeah, form a right angle. Good. Okay. Is angle AXB adjacent to angle, it's supposed to be angle CXD? No, opposite, right? So they don't share a side, do they? Okay. So biconditional statements. Conditional statements are always written as if-then statements. If it's a biconditional statement, if we know that we can read it both ways, we can instead write it using the words if and only if. Okay, so for example, this isn't my original PowerPoint. I think there's something in here. I think this part is actually wrong. You tell me if you agree with me. If this is the statement, it is Saturday only if I am working at the restaurant, conclusion. I mean, this is not a big deal, but what would you probably choose if I had given that to you 15 minutes ago, that statement, and you had to write it as a conditional statement? What would you have said was the hypothesis? Yeah, because it uses the word if, don't you think? To me, that's a little bit goofy. Now, we're going to see that it doesn't really matter in this case. In just a second, we'll see why. But to me, doesn't this, because it uses the word if, this really should be the hypothesis. If I am working at the restaurant, then it's Saturday, right? Because the word if starts here. So this really should have been, I guess they did do it that way, didn't they? No, they didn't. See, this should have been conclusion, and that should have been hypothesis. But if we write it either way, let's think of writing it as this way. If I'm working at the restaurant, then it's Saturday. Isn't the converse also going to be true in that statement? Would you agree? Okay. And maybe the way it's written, if it is a Saturday, then I will work at the restaurant. Because I guess you could be Saturday when you're not working at the restaurant. Maybe if we wrote it that way. If it's a Saturday, then I will spend time working at the restaurant. Would be a better way to maybe say this. If that's always true, then that's a biconditional statement, and so I could write it in either direction, and it really wouldn't matter, right? So what I would do then is I would just say, if it's Saturday, it is Saturday, if and only if I will work at the restaurant, or if I'm working at I work at the restaurant if and only if it's Saturday. Okay, that's kind of a poor example. Let me think of a better one. That one's kind of messed up. How about, we'll use the brunette one. What was the brunette one? What was our original conditional statement? Yeah, if you have brown hair, then you are a brunette. True. But if I turn it around and I look at the converse of that, it's also true, right? So this statement plus if you're a brunette, then you have brown hair, can be combined in the biconditional statement, you have brown hair if and only if, what? You are brunette. Yeah.
You're no longer a brunette.
Okay? Does that make sense? So we can combine, if we know that there's a statement that can go both ways, we can indicate that. We can show that this conditional statement works forward and backward by changing the language to instead say if and only if. The symbol for that in math is just this. An if with two F's in math, that just means if and only if. Okay? All right. What else is this? So if we take, for example, let's take this biconditional statement. 3 lines are coplanar if and only if they lie in the same plane, right? We could, that's 2 conditional statements in one. If 3 lines are coplanar, then they lie in the same plane, or if 3 lines lie in the same plane, then they're coplanar. It includes both of those, 2-for-1 deal. Biconditional statements can be either true or false. Okay, to be true, we've looked at true examples. To be true, both the conditional statement and its converse must be true. Okay, and that's what examples we've looked at. But this guy right here, consider the following statement. X equals 3 if and only if x squared equals 9. Is that true? No, that's not true, is it? Doesn't work, does it? Does it work in one direction? It does, doesn't it? The original, if I leave it in this order, if I were to say, if x equals 3, then x squared equals 9, is that true? That is true, right? But if I try to do the converse, if x squared equals 9, then x equals 3, that's false, right? So is this a valid biconditional statement? No, it's not. It's not. Okay? All right. Try this. Each of the following is true. Write the converse of each statement and decide whether the converse is true or false. If the converse is true, then it's a biconditional statement, right? So we could write it as a biconditional statement. If it's false, we want to show why. Come up with a counterexample. So I'm telling you that the original is true. If 2 points lie in a plane, then the line containing them lies in the plane. Okay, try to visualize that. So the board is a plane, right? If 2 points lie in a plane, then the line containing them lies in the plane. What would the converse of that statement be? Okay. It's kind of, you gotta be a little careful stating it. What do you think? What's the converse gonna be?
If the plane containing the lines has the line, just lie on the plane.
Okay, what's the hypothesis right here, Avery?
If the line containing.
You know, you're right, because, go ahead, you're gonna flip it around. So in this, in the way it's stated right now, what's the hypothesis?
Line containing.
No, the way it's written right now. It'd be the if part, right? If is hypothesis?
Yeah.
Okay, so 2 points lie in a plane.
Yeah.
The conclusion is,
The line.
okay, line containing them lies in the plane. So if I wanna do the converse, what do I do? This-
Line
this question.
containing the 2 points lies in the plane, and the 2 points are in the plane?
Yeah, that's kind of a weird thing to say, but that's it, isn't it? Right, we're saying if a line containing 2 points lies in a plane, then the 2 points lie in the plane. Kind of strange. Is that true? Yeah, that's true, isn't it? Right? Definitely true. And so the biconditional statement would just be 2 points lie in a plane if and only if the line containing it lies in the plane. Is there another way I could have said that by conditional statements? Is there another way? Kirk, is there another way I could have said that that would have worked? Right, and this, we said that this was the original hypothesis and this was the conclusion. Yeah, sure, we could flip them though, couldn't we? Because if it's biconditional, the hypothesis and conclusion are interchangeable, right? The if and only if stays in the middle, but we could flip-flop the hypothesis and conclusion because it's biconditional, right? It has to read both ways. Good, make sense?
Yeah.
Okay, isn't this kind of weird? I mean, it's just logic. Okay, what about this one? If a number ends in 0, then the number is divisible by 5. Okay, so I wish this wasn't all up here. I didn't think it was going to do this. So what's the converse going to be then? Okay, if a number is divisible by 5, then the number ends in 0. But that's not true, is it? Right? Does that make sense? Okay, so for example, they gave, I wish they would have done this, but they gave us a counterexample, didn't they? You see that this is a counterexample? 25. We're looking at the converse now, right? We know that the original statement is true. That statement is true, but the question is, what about the converse? Is the converse false? How do we show that it's false? Well, we can't just say it's false. They're not going to take our word for it. Say it again. Oh, good. So we give a counterexample to prove it. Right. So if we can provide one counterexample, then we showed that the converse is false, and we did. 25 is our counterexample. Okay. Okay. What about a postulate? Let's just take one. We're just about done. And I think when are we done here? At 20. Okay, I want to leave a little time just for a little trivia at the end. So we'll think this will be the last little thing we'll do. The second part of the segment addition postulate is the converse of the first part. Okay, combine the statements to form a true biconditional statement. So we all know the segment addition postulate. If B lies between points A and C, then the length of AB plus the length of BC equals the length of AC. Okay, so is that true? If the length of AB plus the length of BC equals the length of AC, then B lies between? Yeah, it has to be true, doesn't it? Right? So we can combine those statements, and we could make that into a biconditional statement, and that's really that's what we did. If you might remember when we looked back at that postulate, it was written that way. It was written as you can go in either direction with it. Okay. Anyway, brief introduction. You got some. I'm going to give you some short kind of assignments to do. This should not. I mean, has anybody done the first assignment? How long did it take? Yeah, like 5. I mean, that's all it is. They're really short. It's kind of important to do, but it's not going to be much work at all.